Good morning. So in this video, I will discuss some cooling load problems as we discussed in the last class how to calculate cooling load estimation for the given air conditioning room. What is cooling load? What are the components of cooling load? What are the sources for sensible heat load? What are the sources for latent heat load? Then we already discussed about the cooling load procedure for any type of air conditioning problem. Then we discussed about room sensible heat factor, then grand room sensible heat factor by considering infiltration load. Then we discussed about effective room sensible heat factor by considering bypass factor. Right now, see how. Let us see one problem. This is the problem given. So, an air conditioning auditorium is to be maintained at 27 degrees centigrade dry bulb temperature and 60% relative humidity. These are the conditions. Ambient condition is 40 degrees centigrade dBT and 30 degrees centigrade WBT. The total sensible heat load is 1 lakh kilojoule per hour, whereas the latent heat is 40,000 kilojoule per hour. 60% of retin air is recirculated and mixed with 40% of makeup of air. Makeup of air means fresh air. Makeup of air means fresh air. The condition of air leaving the cooling coil is 18 degrees centigrade. So this is 0.4, and design conditions are given as 27 degrees centigrade, 60% RH. This is called as indoor conditions, number 2. And dry bulb temperature is given as dry bulb temperature is given as 40 degrees centigrade, wet bulb temperature 30 degrees centigrade. These are called as ambient conditions are mentioned. It is called as 1. So we will calculate room sensible heat factor based on the given heat loads. There are two heat loads. One is sensible heat load, that is 1 lakh kilojoule per hour, and latent heat load 40,000 kilojoule per hour. So we know sensible heat factor as room sensible heat by room sensible heat plus room latent heat. So 1 lakh by 1 lakh plus 40,000, we will get 0.714. So we will get 0.714, and whatever the value obtained as room sensible heat factor, we assigned as small a. A is called as room sensible heat factor value. So this is 0.714. Okay. Next, condition of air entering the auditorium. So the problem can be represented in a line diagram. Look at here. One is called as atmospheric air conditions, that is 40 degrees centigrade, 30 degrees centigrade, dBT, WBT respectively. Outside air is entering to the cooling coil. So when it is leaving the cooling coil, its temperature is 18 degrees centigrade. So at leaving, this is called cooling coil, and after passing, it is 18 degrees centigrade. So you need to mention 18 degrees centigrade, and this is 2. Then after leaving the cooling coil, it is mixing here. It is mixing here. Then 3 is called mixing of air with recirculated air. Fresh air and recirculated air mixing at 0.3. That is unknown condition. Then after mixing, it is passing through the auditorium. This is called as design space or indoor conditions, which are given as 27 degrees centigrade, dBT, 60% RH. And part of air is removed to the atmosphere through ventilator, and 60% is returned to the mixing point, right? So the diagram can be shown. Look at here. So at 40 degrees centigrade and 30 degrees centigrade WBT, locate, this is 0.1. So first locate 0.1 on the psychrometric chart, right? At 40 degrees centigrade, 30 degrees centigrade, WBT. WBT lines are inclined lines, and 40 degrees centigrade line is vertical line. So locate 1 here. Then we are having right hand side, there is a sensible heat factor scale. So as we are getting, this is 1 and this is 0. At 0.714, locate a point as like this and assign as A, which is equal to 0.714, right? Then we are having small circle in the psychrometric chart. This is B. So how do you identify this circle B? It is 25 degrees centigrade dBT, 50% RH. So 50% RH. So 50% RH. At this point, we are having 25 degrees centigrade. This is 25. So 25 degrees centigrade and 50% curved line. So this is RH line. 50% RH line. So intersection point we will get B. Then by using A and B, you need to join this. A straight line, you need to join this. And you already located the condition as outdoor condition 1 and indoor conditions. So points are different, is deviated here. So this is called as inside conditions. Earlier we noted as 2, but here it is 4. Don't worry about representation of points. 4 is called as inside conditions of the air. That is 4. What is given? 27 degrees centigrade dBT and 60% RH. This is 60% RH. So 4 is located. This point is located, and 4 is located. B is located. A is located. Next step is from point 4. We need to draw a line in which it is parallel to the line AB. Approximate method. From point 4, just draw a line which is parallel to the line AB. These two are parallel. These two are parallel. So we will get this line. So I am drawing this line from point 4 towards saturation curve, which is parallel to line AB, so that I will get 0.5. This is called 0.5. Then condition of air leaving the coil is given as 18 degrees centigrade. So at 18 degrees centigrade, we are having 18 degrees centigrade dBT value. At 18 degrees centigrade, just draw a vertical line. Then automatically it will intersect the line 4, 5. So intersection point is called as 2. This is the point 2. Right? Once you locate point 2, then join 1, 2. Join 1, 2 and extend it. It will intersect the saturation curve. That is called 6, which is called as ADP. And at point 6, at point 6, at point 6, this is called point 6. You need to read the value here also or here also. We will get directly get the ADP value, right? So this is the way you need to represent the given problem on psychrometric chart. I'm once again repeating. So first locate point 1. How to locate point 1? DBT 40 degrees centigrade vertical line. So you need to take the psychrometric chart and 30 degrees centigrade WBT line. So intersection point is 1, right? Then locate point A on the sensible heat factor scale. So A value obtained as 0.714 and B is identified as already small circle is there in the psychrometric chart. So 25 degrees centigrade, 50% RH. So 50% RH. So 50% RH here and 25 degrees centigrade dBT. So we will get point B. Then join line AB by using straight line. Once you draw the line AB, then with respect to, you need to join 1, 4. By using scale, join 1, 4. Straight line. Then from point 4, draw a line towards saturation curve parallel to the line AB. Then we will get line 4, 5. Since condition of air leaving the coil is given as 18 degrees centigrade, at 18 degrees centigrade, draw a vertical line which will intersecting the line 4, 5, that is called as 2. Then join 1, 2 and extend it. It is called as, we will get 0.6 here, ADP. And this line is called as grand sensible heat factor line. And line 4, 5 is called as room sensible heat factor line. After the coil, there is a mixing. How do you mix? 60% of written air with 40% of makeup of air. Then first you need to measure this length of 2, 4. I need 0.3, but 0.3 is unknown. Then length of 3 from 0.2, length of 2, 3 is equal to percentage of recirculated air by total percentage of the mixture, right? So that will be discussed here. So length of 2, 3 by length of 2, 4. You need to measure the length of full length of 2, 4 and the length of 2, 3. Because we are moving from point 2 to point 4, then length of 2, 3 by length of 2, 4 is equal to percentage of recirculated air by total percentage of the mixture. So percentage of reacted air is 0.6. By total percentage means 0.6 plus 0.4. So it is 1. So 0.6 by 1, 0.6. Then length of 0.3 from 0.2 equal to 0.6 into length of 24. So measure this inclined length of 24. Let it be 6 centimeter. Then 0.6 into 6, 3.6 centimeter. Then from point to at a distance of 3.6 centimeter, you need to locate a point that is called as 3, which is called a mixing point. At that point, if you draw a vertical line, it gives dBT. If you draw a inclined line, it gives enthalpy value, right? So after locating point 3, dry bulb temperature 23 degrees centigrade, wet bulb temperature 19.5 degrees centigrade, relative humidity 72%. In this way, we can calculate mixing point. Is it clear? Since the mixing is given as 60% reserved layer with 40% makeup of air, point 3 is located as length of 2,3 by, we don't know 3. That's why length of 2,3 by length of 2,4. But length of 2,4 is known, is equal to percentage of recirculated air by total percentage of the mixture. Percentage of recirculated air 0.6 by 0.6 plus 0.4, it gives 1. So 0.6 by 1 into length of 24. If we multiply, we will get some value that is measured from 0.2 at a distance of length of 24 of 0.6, so we will get 0.3. At that point, just draw vertical line, it gives dBT. So values are obtained as 23 degrees centigrade dBT, 19.5 degrees centigrade WBT, 72% relative humidity. Then we need to calculate the amount of fresh air, how much quantity of fresh air is added, right? For that, from psychrometric chart, read the enthalpy values at H4 and H3. Read the enthalpy values at H4 and H3 from the psychrometric chart at H4. So this is an inclined line. We will get H4 and H3 as 61 and 56 directly. 64 and 66. Then we need to calculate mass of total air supply to the auditorium. Mass of total air supply to the auditorium is given as room total heat by this difference of H4 minus H3. So room total heat means room sensible heat plus room latent heat. So 1 lakh plus 40,000. 1 lakh 40,000 by 61 minus 56. So it is 28,000 kg per hour. So the amount of total air supplied to the room is 28,000 kgs of air supplied per hour. But only 40% is supplied air as makeup of air. Therefore, mass of fresh air supplied to the room is 40% of 28,000. So 0.4 into 28,000, it is 11,200 kg per hour. In this way, you need to calculate mass of fresh air. Then operator's dew point you need to evaluate. So operator's dew point already taken from the chart. So when you join 1, 2 and extend it, we will get 6. At 6 point, we are having directly read the value on saturation curve, or you need to draw a vertical line. So value is 13 degrees centigrade. Then finally, you need to calculate the bypass factor of the cooling coil. Bypass factor is nothing but inefficiency of coil. How much efficiency? 1 minus bypass factor is called the efficiency of cooling coil. So bypass factor is given as, if you take the line, so this is the line 1 to 6. So actually coil is 100% efficient, then automatically coil is reaches the temperature ADP, but it may not reaches here, it is reaches only 2 point. What is temperature lagging? T2 minus T6. And what is total temperature difference? It is T1 minus T6. So T2 minus ADP by T1 minus T6, that gives bypass factor. Since T2 is given as 18 degrees centigrade, ADP 13, and T1 is 40, and it is 13. So we will get 0.185. That is bypass factor. That is bypass factor. So bypass factor for this problem is 0.185. So if you want to calculate efficiency of coil, then it is 1 minus bypass factor. So 1 minus 0.185, that gives efficiency of coil. So this is the way you need to solve the given problem. Is it clear? So I will summarize the solution for the problem. So whenever a problem given on air conditioning, so in this problem, first you need to calculate room sensible heat factor. So how do you calculate room sensible heat factor? So it is the ratio of room sensible heat by room total heat. So 1 lakh by 1 lakh 40,000, 0.714. And later I will represent the line diagram for the given problem. So inlet is outdoor conditions 40, 30. Then it is passing through cooling coil. After cooling coil, it becomes 18 degrees centigrade. Then it is mixed with 60% recirculated air. Then it is circulated in the auditorium. And this is the psychrometric chart where we need to represent all the properties. So first locate point 1 as 40-30. Then locate point 4 as 27-60% relative humidity. Then locate point E on the sensible heat factor scale of value 0.714. So we are having point B as base circle and join AB. From point 4 with respect to line AB, you need to generate a horizontal parallel line with respect to line AB, and we will get 5 here. As supply condition of air is leaving is 18 degrees centigrade, 18 degrees centigrade, dry vertical line which will intersect line 4, 5. So we will get 0.2. Right? So join 1, 2 and extend, we will get 6 here. So 6 is called ADP, that is 13. Then you need to calculate the length mixing point. How do you calculate mixing point? Since 60% is recirculated air is given, 40% makeup of air is given, length of 23 by length of 24 equal to percentage recirculated by total percentage. So 0.65, 0.6 plus 0.4, it is 0.6. So length of 23 equal to length of 24 multiplied by 6, we will get the values at 0.3 is 23, 19.5, 72% respectively. So amount of makeup of air. For that, we need to use some relation. Total mass of air supplied is given as room total heat by the enthalpy difference of H4 minus H3. So we will get 28,000. But only 40% is makeup of air. So 0.4 and 28,000, that gives 11,200. ADP from the psychrometric chart as 13 degrees centigrade. Bypass factor of the cooling coil is T2 minus. So this is actually one is outside air that is passing through cooling coil at 13 degrees centigrade, but it is not reaching 13, but is only 18. So there is an inefficiency. How much inefficiency? That is given as T2 minus T6 by T1 minus T6, where T6 is called as ADP. So we get 0.185. So there is another simple problem here. A conference room for seating 100 persons is to be maintained at 22 degrees centigrade DBT, 60% relative humidity. And the outdoor conditions are given as, the outdoor conditions are given as 40 degrees centigrade DBT and 27 degrees centigrade wet bulb temperature. So various loads on the auditorium is given. Sensible latent heat load per person is 80 watts and 50 watts. So sensible heat load is 80 watts per person. How many persons? 100 persons. If you want to calculate total sensible heat, then 80 into 100, it is 8,000 watts. Similarly, latent heat 50 watts per person and total persons are 100 into 50, it is 5,000 watts. Light spans 1500 watts. Sensible heat gain through glass wall ceiling 1500 watts. Air infiltration. Infiltration load is given 20 meter cube per minute. Fresh air supply 100 meter cube per minute. 2/3 of recirculated room air and 1/3 of fresh air mixed with before entering the cooling coil. This is important. Earlier problem it is after cooling coil. Here it is before cooling coil. Bypass factor also given as 0.1. Determine ADP, global grand total heat, effective room, sensible heat factor. So the flow diagram is shown here. So first we need to take outside air, that is 40 and 27 degrees centigrade DBT WBT. And then it is directly entering into the mixing coil. So mixing point is 3. Then after mixing, it is passing through cooling coil. Then it is passing through the design room where the temperatures are 22 and 60% RH. And here only 2/3 is recirculated, one third is taken as fresh air, and 2/3 is recirculated here. So you need to locate points. As one is given as 40, 27, and the 2 point is given as 20 to 60%. Locate points from psychrometric chart. After locating 1 and 2, we will get the specific value is 0.911, H1 85, H2 47.5, and HA 66. How to take HA? I will show here. So we need to locate 1 here. So this is 0.1 as 40 and 27 degrees centigrade, and locate 0.2 here. So as locate 0.2 here, it is 22 and the relative humidity is 60%. Then we need to join 1 to here. You need to join 1 to here. So we are joined 1 to. And this is called alignment circle as 25 degrees centigrade dBT and 50% RH. So this is point B, and you need to calculate this A, that is room sensible heat factor, which is evaluated as 0.79. I will show you how to calculate room sensible heat factor. At point 1, we already taken the specific volume value like this we are having. So where specific volume V1 is given as 0.911, where volume of air supplied to the room is 20 metric cube per minute. So 20 by 0.911, it is 21.95 kg per minute. So mass of air supplied to the room is 21.95. 21.95. So sensible heat gain due to infiltration. So sensible heat gain due to infiltration means mass of air into HA minus H2. So if you look at the previous slide, so here we will get point 1 and point 2. From point 2 draw a horizontal line, and from point 1 draw a vertical line. So we will get point A as intersection point. From H2 to HA to H2, so there is an increase in temperature because of the heat is added. It is called as sensible heat. From 1 to A, so only temperature remains constant, but there will be change in omega. It is called as latent heat. So for that, so we need to calculate sensible heat gain due to infiltration air. So M1 into HA minus H2. Since H1, H2, HA value are already taken, so it is 406 kilojoule per minute. So divided by 60, it is 6.77 kilowatts. Similarly, you need to calculate latent heat due to infiltration of air. What is latent heat due to infiltration of air? So mass of air is at point 1 is already taken. Then infiltration load is M1 into H1 minus HA. So M1 into H1 minus HA, so it gives 417 kilojoule per minute divided by 60, it is 6.95 kilowatts. Then total sensible heat gain from persons. So each person 80 watts, and there will be number of persons are 100, so 8,000, it is 8 kilowatts. Similarly, total heat load. So each person is 50, there are 100 persons, so it is 5,000 watts, so 5 kilowatts. Therefore, total room sensible heat equal to, you need to add all sensible heats given in the problem. So it is 6.77 initially, then we are having 8, then we are having 15, 15. It is due to sensible heat due to fan, sensible heat due to glass, walls, ceiling. It is given in the problem. So it is 44.77, that is room sensible heat load. Similarly, you need to calculate room latent heat load. So room latent heat load is given as due to infiltration and due to persons. So 6.95 plus 5, it is 11.95. Therefore, room sensible heat factor is given as room sensible heat by room total heat. So if you simplify, it is 0.79. That is already shown in the cyclomatic chart. This is 0.79. This is the way you need to calculate room sensible heat factor. Then in the given problem, it is states that only 1/3 of fresh air is mixed before entering the cooling coil. So 2/3 is recirculated. We need to calculate length of 2/3 equal to length of 1/2 into 1/3. Only 1/3 is fresh air and 2/3 is recirculated. So length of 2/3. So from point 2 at a distance of 3, you need to locate 3. Length of 2/3 equal to length of 1/2 into the percentage of fresh air by total percentage of the mixture. So we will calculate length of 2 1 into 1/3, and we will so we will get some value. Then locate the point 3 where the arrival temperature at point 3 is 28 degrees centigrade. So once you locate the point 3, then so T6 is called as operator's dew point temperature. It is called as ADP. We know bypass factor. What is bypass factor? So bypass factor is given as 0.1 in the problem. So T4 minus T6 by T3 minus T6. So if you look at the diagram, so 3, 4, 6, 3, 4, 6 is called as the cooling process. So if bypass factor is 100%, then automatically 4 and 6 is 1, but it is only 0.1. So we are having bypass factor equal to 0 means coil efficiency 100%. 4 is also equal to 6, but it is 10% bypass factor means 90% efficient. So T4 minus T6 by T3 minus T6, that is called as bypass factor, which is equal to 0.1. Where here bypass factor is known as 0.1, T4 is unknown, T6 unknown, and 28 is given. So by trial and error method, we will calculate T4 as 13.15 degrees centigrade, T6 as ADP 11.5 degrees centigrade. So infiltration load is also given. So for that, we need to calculate outside air total heat. So outside air total heat is given as 0.02 V1 into H1 minus H2. 0.02 into volume is given as 20, H1 minus H2 known, so it is 15 kilowatts. Then grand total heat equal to room sensible heat plus room latent heat plus outside air total heat. So if you sum up all, we will get 71.72 kilowatts. 71.72 kilowatts. Then join 6 with point to produce up to sensible heat factor scale on the psychrometric chart. The line 6.2 known as effective room sensibility factor line, and the value is 0.77. We know how to calculate effective room sensibility factor. Effective room sensibility factor equal to effective room sensibility by effective room total heat. So if you use that relation, we will calculate as 0.77. And this is represented as, so if you join 6.2, we will calculate effective room sensible heat factor line. So effective room sensible heat is effective room sensible heat by effective room total heat. Okay, thank you.